Alright, this is chapter 6, section 3, and we're talking about vectors. If we saw the movie Despicable Me, there was a character named Vector, and he says something along the lines with, my name is Vector because I have magnitude and direction. That actually is the definition of a vector. So an example would be, say, we're on an incline. And this is us. And we're going up, say, a little hill right there, and we're pulling some kind of something, doesn't matter what it is. So we're pulling something up that incline, however much that is weighing. So let's say that's 25 pounds. That's the magnitude of, say, so 25 pounds. So 25 pounds would be the magnitude of whatever it is that you're pulling up that incline. And the direction, let's say that's 15 degrees is our incline. So now we have our magnitude of whatever we're pulling up and the direction at which we're pulling up the cart or whatever you're dragging uphill. So again, a vector has magnitude and direction. So how can we calculate that magnitude and how can we calculate that direction? The magnitude, if we're, let's say, on the coordinate plane. For instance, take a look down here. Okay, so I have two vectors, and typically when we label vectors, we use these bold-faced letters. So this bold-faced U, we're talking about vector U. It has an initial point here, terminal point here. Then we have vector V, initial point, terminal point. Okay, so a vector, again, has magnitude and direction. So how am I going to measure the magnitude and the direction of, say, something that's on the coordinate plane? So if we're looking strictly at V, magnitude would be the distance from here to here. And direction would be the slope. So let's write that down. All right, so again, magnitude is calculated with the distance formula, and direction is going to be calculated with the slope formula. So I'm actually interested in determining if these two vectors are what their magnitude and what their distance are. So let's go ahead and actually find the distance from initial point, terminal point for each of these vectors and the slopes, and then we're going to compare them. So I'm going to start with vector U, and usually we annotate magnitude with these two, looks like absolute value bars, but it's twice there, so that is the annotation for magnitude. Remember, distance formula is the change in x. So I'll actually write that up here. Distance equals x2 minus x1 squared plus y2 minus y1 squared. And then remember, slope is equal to change in y over the change in x. All right, so we're finding the magnitude for vector u. So difference in x, so 0 minus -3, and I'm going to square that, plus the difference in y. 3 minus -3, and we're going to square that. So here we get, all right, so here we end up with 3 squared, 9, and then 3 plus 3 is 6, squared is 36. That's square root of 45, so that's 3 root 5. And that's the magnitude of vector u. So now I'm interested in the direction. So I'm going to do the slope. So that's 3 minus -3 over 0 minus -3. And I get 6 over 3, which is 2. And now I'm interested in vector v. So let's start with the magnitude of vector v. We're going to have 3 minus 0 squared plus 6 minus 0 squared. Notice that we're going to get 3 squared, 9, 6 squared, 36. I'm going to get square root 45. I just realized I didn't write 3 root 5 here. And I get 3 root 5. And now I'm interested in the slope. We can again count, and clearly it's up to over 1, but let's just make sure we remember the formula. Change in y, so 6 minus 0 over 3 minus 0, change in x, and we end up with 2. So notice that the magnitude of vector u and the magnitude of vector v, and the slope of vector u and the slope of vector v are equivalent. When these components are equal, we say that the vectors are equal. So we could say that u is equal to v. So again, vectors that have the same magnitude and direction are equivalent vectors. Okay. We have a couple ways that we can express vectors, and one of them is called component form of a vector. Basically is where we have these fancy annotations, so we have these special symbols where we're expressing. And what we're going to do is we're going to take the terminal point and the initial point, subtract them, and get what we call the component form. It's really important to take the terminal point and subtract the initial point in that order. And what this is doing is repositioning our vector. So for instance, say our vector is somewhere here in space, going in that direction. Okay, what I'm going to do is I'm going to take that vector, I'm going to reposition so it starts at the origin. We're going to pretend that these are equivalent. And so I took this vector and I repositioned it here. That's the component form of a vector. We took the vector, we put it so that its initial point is at the origin. All right, so recapping. Magnitude, again, that we use finding the distance formula. If we're in component form, this should say somewhere over here. This is what I'm referring to when I'm in component form. This is a special annotation that I was talking about, and the symbol should be magnitude. Then I can shortcut the formula because my initial point's at the origin. So therefore we could just say a squared plus b squared. Take the square root of that, and that is our magnitude. Something else that I want to note is when we're in component form, if two vectors have the same component, then they're equal as well. So another way to show that u is equal to v, other than comparing their magnitude and comparing their direction, is to actually put them in component form. So u, look, it's already at the origin. So that's already in component form, so let's just express it in component form. Done. Here, I want to rewrite this so that it is in component form, and if the components are equal, then u is equal to v. So again, when we're solving for component form for vector v, we do the terminal point, which is -2, -1. So -2 minus -4, that's our first a part, and then b, -1 minus -4. Let's simplify that. Here I end up with 2, and here I end up with 3. So notice that they are in fact equal. This was much faster than finding their magnitude and the slope of each. So I can compare them based on the component form. So u is in fact equal to v. Okay. All right, so let's make sure we understand how to put this into component form. Again, we're going to take the terminal point, combine the x's only, and then combine the y's only. And remember, it has to be terminal minus initial, so this is going to be 16 and 7. That does not look like 7, so vector v is equal to that here. 5 minus -3, 1 minus -5. Re-express it, here we get 8 and 6. Alright, so we can scale our vectors, rescale them. So for instance, if the black vector line segment is amplified by 2, you can clearly see that the magnitude is doubled. If we multiply it by a fraction between 0 and 1, you can clearly see that the magnitude is reduced. And then if you multiply it by a negative, you can see that it goes in the opposite direction. So that's exactly what we're doing. Vector addition and scalar multiplication. So when you're adding them, you're literally combining the terms for what would be x and the terms for what would be y. Whether we're adding or subtracting, when we have a scalar multiple, everything gets affected by it, and including a negative. When we're sketching a vector, remember that the first component, think of this is in component form, so you would plot your initial point at the origin and say that we had 1, 2 is vector v. So then I would plot 1, 2, and that's how you would sketch that. So there's x, there's y, here's our origin, 1 and 2. So let's take a look at this example. It says we're going to find the addition, the difference, we're going to take twice u minus 3 times v, then we're going to sketch each resultant vector. So let's start with the sum. So we're going to do u plus v. So we're going to do 2 plus 1, 1 plus 3. And we end up with 3, 4. And now let's sketch that because that's what the instruction said to do. Remember, you start with your initial point at the origin. And there's our terminal point. We're going to pretend I connected the dots. And now we're going to do u minus v. So now we're going to subtract them. 2 minus 1, 1 minus 3. So what I'm plotting is the resultant vector. So if I were to graph 2, 1, here's 2, 1, and 1, 3. In between them is the resultant vector of the sum of u and v. So that's what's going on here. So here I have 2 minus 1, 1, 1 minus 3, negative 2. Let's go ahead and graph that. Remember, we start with the origin because this is in component form, and then terminal point. And now I'm going to do twice u minus 3v. Well, in order to do 2 times u, let's just find 2u. So I'm going to take vector u, and I'm going to multiply it by 2, and we're going to get 4, 2. And I'm going to do 3 times u, or was it 3v? It was 3v. 3 times v, and that's 3, 1, 3. And we're going to get 3, 9. And now we want the difference, 2u minus 3v. So that's going to be 4 minus 3, and I'm looking over here because we already solved those components. 4 minus 3, and 2 minus 9. So that's 1, negative 7. So let's go ahead and graph that. Remember, your initial point's at the origin. Here's our terminal point, and we're going to pretend it's pretty. So that would be graphing the resultant vector. Okay, another way to express vectors are in terms of I and j, and this is called a linear combination. So we have the component form, and now we have the linear combination of vectors I and j. So why is it important to express in terms of I and j? Is because we're going to do something important in just a minute called a unit vector. So we have our horizontal component. That's going to be in multiples of I. And then we have our vertical components, which are going to be in terms of j. And notice that the magnitude is still the same because our initial point is still at the origin. So for instance, this is branching off, let's say vector v is 1, 2, and we're in component form. If we're expressing that in terms of I and j, it's the same thing. So that's going to be 1i plus 2j. So the concept's still the same, and we can still use the same formula that we used to shortcut for the component form for terms of I and j for the linear combination. Okay, so let's take a look. We're going to do exactly the same thing, and we're going to sketch the resultant vector. So now I have it in terms of I and j. I personally think this is easier because it's kind of like algebra when we're adding them. So when I'm doing u plus v, I'm literally going to add like terms. So here I have this. My like terms are the j's. So I get 3i plus 3j. Let's graph that. Initial point at the origin, terminal point at 3, 3. All right, now we have subtraction, so I'm doing u minus v. So again, 3i plus j minus 2j. So we end up with 3i minus j. And when we graph that, Here's x, y. Our initial point 0, 0, terminal point 3, negative 1. And now we're going to do, it was 2u minus 3v. So I'm going to do 2u. Okay, so here would be 2u minus 3v. I like to set it up by distributing this 2 to each term, this negative 3 to each term, combining like terms. Remember, initial point here, terminal point here. If we're putting in component form, this is the equivalent of it. Here's just a brief recap. When I'm taking the difference, we're literally just combining like terms. We end up with 3i minus j, initial point, terminal point 3, negative 1. All right, so remember that our horizontal distance was I, our vertical distance was j, and now those are going to be your 1 unit increments in terms of I and j. So 1 unit I, 1 unit j here. If I'm in terms of I and j, I want to find the unit vector in the same direction. So for instance, if I have v equals 2i plus 4j, and I want the unit vector of what I just wrote there, unit meaning 1. So for instance, if you buy a 12-pack of soda and you want to know the unit price of each can, what would you do? You would take the price, you would divide by 12. The concept is the same here. You want the unit vector 1. So the unit vector is going to have, because it's a unit, a magnitude of 1. So the formula is take your vector and divide by its magnitude. So here's our vector, or magnitude. Remember the magnitude for vector v, square root of a squared plus b squared. So that's going to be 4 plus 16, square root 20, which is 2 root 5. And so what do? We take our vector and we're dividing by the magnitude, so 2 root 5. And I'm going to go one step further. We're going to break up each fraction. We're going to simplify where possible. So 2i, 2 over root 5, plus 4j, 2 over root 5. And here we can see the 2's reduce. Here this becomes 2. Then we rationalize the denominator, because what we have is 1 over root 5 I, and we know we don't leave that there, 2 over root 5 j. And so our answer for our unit vector here is going to be root 5 over 5 I plus 2 root 5 over 5 j. Okay, so here, what did I just find? I found my unit vector. If I were to find the magnitude of the unit vector, it's going to equal 1, and that's what I said a moment ago. So let's do the magnitude here, and this is our unit vector, by the way, so I'm going to write it like that. The magnitude of the unit vector is equal to a squared plus b squared. And b squared. So let's go and simplify that. Root 5 squared is 5 over 25. Here we're going to get 4 times 5 over 25. And then we could see that we get 25 over 25, which equals 1. So we know we did it right. So we want to verify that we did it right after we find our unit vector. How do we do that? We find the magnitude. All right, here's an example. It says find the unit vector in the same direction as the given vector. Verify that the result has a magnitude of 1. So let's go ahead and do that for A. So again, we need the magnitude of u. Shortcut, a squared plus b squared. So that's going to be root 10. Then take your vector, divided by its magnitude. So that's going to be 1, negative 3, root 10, separate it. rationalize it. And now we want to verify. Again, remember this is your unit vector. Now I want to find the magnitude of my unit vector. A squared plus b squared. So I'm going to get 10 over 100 plus 9 times 10 over 100. And then this is going to be 90 plus 10 is 100 over 100, which isn't equal to 1. So we did it right. Okay, now let's do the same thing, but in terms of I and j, so we can get a little variation of the different ways we can express this. So first I need to start by finding the magnitude here. So negative 3 squared plus negative 4 squared. So that's going to be 9, that's going to be 16. 16 plus 9 is 25, so the magnitude's 5. This one's easier. So now I'm going to find my unit vector. So that's negative 3 over 5i minus 4 over 5j. So that's our unit vector. Let's verify it. So now I'm finding the magnitude of the unit vector. Square root of a squared plus b squared. So here we get 9 over 25 plus 16 over 25 equals 25 over 25. That's 1. So we know we did it right. So just recapping, I want to make sure that you're able to write in terms of I and j. So we have our terminal point. So remember, let's call this vector v. What we're going to do, remember, it's terminal minus your initial point, and it's I, plus, now we're looking at the y's, terminal minus initial point j. So here we get 4i plus 5j. All right, so something else I want to talk about is the components a and b. So let's say I have vector v equals ai plus bj. We can take those components a and b and we can express them in terms of the magnitude of the vector and the angle that it's making with the positive x-axis, which we're going to call the direction angle. So for instance, say here's my x-axis, here I have my angle theta, and say this is my vector. Here's my vector, initial point, terminal point, with some type of magnitude, and we're calling those components a and b. So what we're going to do now is we're going to express it in terms of its magnitude and the direction. So some formulas that we use to do that with are as follows. Okay, when we're writing a vector in terms of its magnitude and direction, we let the vector be a non-zero vector. If theta is the direction angle measured from the positive x-axis to that vector, then the vector can be expressed in terms of its magnitude direction, where its vector is equal to the magnitude times cosine theta I, magnitude sine theta j. Okay, and this should say plus, by the way. Plus, right there. All right, here's an example. The wind is blowing at 20 miles per hour in the direction, there should be a degree symbol there, north 30 degrees west, expressed as a vector in terms of I and j. So let's draw a picture. So north 30 degrees west, I know that's right here. Okay, so this is 30 degrees going west, and I have 20 miles per hour. So this is 20 miles per hour, 20. So that's our magnitude. Okay. I should have pointed an arrow at it. So that's 20 miles per hour. I'm interested, remember I said coming from the positive x-axis. So I know that this is 90 degrees here. So I actually have to sum these angles. So when we put it into the formula, we do 90 plus 30, so that angle measurement theta that we're referring to in our formula is actually 120 degrees. So remember, V equals magnitude V cosine theta I plus magnitude sine theta j. And now it's just direct substitution. So here we have 20 cosine 120 degrees I plus 20 sine 120 degrees J. And 120 degrees, that's from the unit circle. So I'm actually going to substitute that with values from the unit circle. So cosine 120 is negative a half I plus 20 sine 120 degrees is root 3 over 2 J. Let's simplify it. We get negative 10 I plus 10 root 3 J. So that's the vector in terms of I and J. So the wind's velocity can be expressed in terms of I and J as vector V equals negative 10I plus 10 root 3J. Here's another example. Find the component form of vector V given its magnitude and the angle it makes with the wind, with the positive x-axis. Sketch V. So it gives us the magnitude, it gives us theta. So really nice. So now we get to substitute it. Remember, V equals magnitude, cosine theta, plus magnitude, sine theta. And find the exact values from the unit circle. So let's substitute. So we get 2 root 3 cosine at 45 degrees is 2 root 2 over 2. 2 root 3 sine 45, root 2 over 2. Simplify. I forgot to put my i's and my j's. So I, j, I, and j. So vector V is equal to root 6i plus root 6j. And then sketch that. All right, so let's find the component form of the sum of u and v. Find the direction angles theta u and theta v. So let's start by finding the component form of u and then the component form of v. So u is equal to the magnitude cosine theta plus magnitude sine theta. And then we could just put it in, and that's I, sine theta j. All right, cosine at 0 degrees. So here we're going to get 5 I, and that's it. There's no j. So if you want to put 0j, that's fine with me. Oh, we're in component form, not in terms of I and j. So 5, comma, 1, 0. Sine at 0, 0 times 5, 0. Now we're going to do the same thing for v. 5 cosine 90 degrees I plus 5 sine 90 degrees j. Cosine at 90 degrees, that's at 0. So in component form, 0. And sine at 90 degrees is 1, so that's 5. So when I do u plus v, I get 5, comma 5. Okay, the instructions also mention to find the resultant angle. This is the formula that we use. Remember, this is A, this is B, so I'm going to do tan theta 5 over 5. So tan theta equals 1. And I know that at 45 degrees, tangent is 1. So that's our answer. All right, so now let's talk about applications to force. So many physical concepts can be represented by vectors. A vector that represents a polar push of some type is called a force vector. If you're holding a 10-pound package, 2 force vectors are involved. The force of gravity is exerting a force of magnitude 10 pounds, so that's that. This is F1. And this force is shown by vector F1. Assuming there's no upward or downward movement of the package, you are exerting a force of magnitude 10 pounds directly upward. So that is vector F2. We're interested in the resultant force of these 2 forces acting on this package. So it has the same, force 2 has the same magnitude as a force exerted on your package by gravity, but it acts in the opposite direction. So what we're going to do is take 2 forces and find the resultant vector. So for instance, two forces, F1 and F2 of magnitude 5 pounds and 12 pounds respectively, act on an object. The direction of F1 is north 20 degrees east, and the direction of F2 is north 75 degrees east. Find the magnitude and direction of the resultant force. Express the magnitude to the nearest hundredth of a pound and the direction angle to the nearest tenth of a degree. All right, what I like to do now is to draw a picture. So we have force 1 is north 20 degrees east. Remember, that's north, that's east. Here's 20 degrees. But what we're really interested in is the angle that comes up in this direction for the formula. So that's going to be 90 minus 20 is 70 degrees. So this is F1. So now and then it tells us that the magnitude is 5 pounds. So I want to write this in terms of I and J. So let's start with F1. So remember, we're going to take its magnitude, cosine theta I, plus magnitude, sine theta j. Tells us the magnitude's 5. We're going to do cosine 70 degrees. I, we need our calculator here. Magnitude, 5 sine 70 degrees j. So let's do cosine 70 degrees times 5. Okay, let's round to two place values. Here we get 1.71 I plus 4.7. I did that backwards. 4.7j. So this is F1. Now I'm interested in F2. So let's draw a picture for that. All right, force 2 was going north 75 degrees east. So here's north, east, about right there. This is force 2. And this is 75 degrees. What we're interested is in this interior angle for the formula. That's 15 degrees. The magnitude here, I believe, was 12. So we have 12 pounds. All right, so this is the formula. So we're going to do, remember, magnitude cosine theta I plus magnitude sine theta j. So the magnitude here is 12 cosine 15 degrees I plus 12 sine 15 degrees j. We're going to put that in our calculator. We get vector 2 is equal to, let's round to two place values, 11.59 I plus 3.11 j. Okay, so at this point, what we're going to actually do is take the first force and the second one, and that's going to be equal to our resultant. Let's try to make that a little bit darker. So that's our resultant vector. And then we're going to find its magnitude and its direction. All right, so what I just did was, here we have the first vector that we solved and the second vector that we solved. So we're literally going to add them, like I said a second ago. Take your terms of I, your terms of j, that's what I just did here, and let's add them. So 1.71 plus 11.59, we get 13.3I plus 4.7 plus 3.11 is 7.81j. So this is our resultant vector. Now we're interested in its magnitude and direction. All right, so what we're looking for here is the magnitude, which is the square root of a squared plus b squared. So we have 13.3 squared plus 7.81 squared, and we're going to take the square root of that. All right, and so what we get is the square root of 237.89, and what we just found was that the magnitude of the two forces acting on the object is 15.43 pounds. So now what we're interested in is the resultant force, or the direction of the resultant force. So we can use two formulas. Cosine theta is equal to A over the magnitude of what we just found, or we can do sine theta, and remember that's going to be B over the magnitude of what we just found. All right, And we specifically take the A or the B from the top. So here we get cosine theta equals 13.3 over 15.43. So that means I'm going to be using arc cosine. Use your calculators. And let's round to two place values. So I get 30.46 degrees. And that's the resultant direction.